everyday macroscopic experience of the world is saturated, as everybody knows, with asymmetries, thermodynamic asymmetries, and radiative asymmetries, and epistemic asymmetries, and phenomenological asymmetries, and asymmetries of overdetermination, and asymmetries of influence, and what have you, between the past and the future. And there's a long cherished hope, something that has its origins in the work of Boltzmann, which has been pursued by any number of other investigators through any number of fits and starts and revelations and wrong turns ever since, that all of those asymmetries can ultimately be traced back to some relatively simple characteristic of the initial macro condition of the universe. The thought, as people put it nowadays, is that all we need to do in order to account for those asymmetries is to add to the fundamental time reversal symmetric dynamical laws and to the standard statistical mechanical probability measure over the space of possible fundamental physical states, a simple postulate, a so-called past hypothesis, to the effect that the world first came into being in whatever particular low entropy macro condition it is that the normal inferential procedures of cosmology are eventually going to present to us. The business of working this thought out in detail is a large undertaking, which is still very much in its infancy after all these years, and which is still very much under debate after all these years. And this is a program which a bunch of the people here have heard me describe on a number of occasions. So I don't want to attempt anything along the lines of an overview of that project here. All I want to talk about today is one of a number of as it were, footnotes to that discussion. And in particular, what I want to talk about is a widespread and fundamental and perennial sort of puzzlement about how such a project could even seriously be entertained. A puzzlement that is about how it is that the macro condition of the universe 15 billion years ago, all by itself, could even imaginably be up to the job of explaining so much about the feel today and on Earth of the passing of time. The puzzlement takes a number of different forms, and it arises in a number of different contexts. On the most trivial level, there's a question about how the lowness of the entropy of the world 15 billion years ago can impose any genuinely profound and vivid constraints, whatever, on what the world is doing now. And all that needs to be said in order to make that sort of puzzlement go away is that although 15 billion years is a long time, the entropy of the universe at that time was very, very low. And that in particular, 15 billion years is a great deal shorter than the expected relaxation time of the state in which our universe seems to have started out. There's a more interesting question about how the lowness of the entropy of the world 15 billion years ago can have any genuinely profound and vivid effects or impose any genuinely profound and vivid constraints on what particular localized, human-scale, quasi-isolated subsystems of the world are doing now. The worry in particular runs like this. Suppose that we grant that the standard Boltzmannian arguments do indeed establish that the overall entropy of a universe, which starts out in a low entropy, past hypothesis sort of macro state, is overwhelmingly likely to rise toward the future. That does nothing at all, so the worry goes, to show that the entropies of quasi-isolated subsystems of the world are likely to rise in the same direction. And it's the behaviors of those latter systems, after all, and not the universe as a whole, that's the central and paradigmatic topic of thermodynamics. Janan Ishmael, who's here, has written in precisely this connection that it should be clear, I'm quoting now, it should be clear that you can't in general move from a property of the whole to properties of its parts. The fact that dogs can run doesn't mean that dog heads can run. Forests expand and babies grow, but not because the trees or the cells that make them up do. The global story just isn't the local story writ large. There are all kinds of ways in which a system could have global dynamical properties that are not properties of any of its parts, close quote. And there's a paper of Eric Winsberg's, who's here as well, in which he worries that the conditions that are required in order to run the standard Boltzmannian argument to the effect that the entropy of an isolated system will increase toward the future might somehow be altogether different from the conditions that are required in order to run the analogous argument on whatever quasi-isolated subsystems of that larger system may happen to emerge as the larger system evolves in time. It's not clear to me that I completely understand what this worry is about or where it comes from, and part of the reason it seemed like a good idea to bring it up here is in the hope of finding out from Janan and from Eric themselves what it is that I might be missing. The way it looks to me is that the Boltzmannian tradition has given us an argument that the overwhelming majority of microconditions compatible with any non-equilibrium macro condition of any isolated thermodynamic system are sitting on trajectories on which all of its thermodynamic properties, and not merely its overall entropy, are going to evolve toward the future in the general direction of equilibrium in accord with our usual thermodynamic expectations. If, for example, the isolated system in question consists of two gases, which are initially at different temperatures and which are in thermal contact with one another, what the Boltzmannian arguments make plausible is not merely that the overwhelming majority of microconditions compatible with this initial macro condition are sitting on trajectories on which the overall entropy of the system is going to increase toward the future, but in addition, that the overwhelming majority of those microconditions are sitting on trajectories on which the entropy of the hotter gas is going to decrease toward the future. And if the isolated system in question consists of, say, 12 isolated gases in 12 separated containers, each of which is initially far from its own individual equilibrium state, then what the Boltzmannian arguments are going to make plausible is not merely that the overwhelming majority of microconditions compatible with this initial macro condition are sitting on trajectories on which the overall entropy of this system will rise toward the future, but in addition, that the overwhelming majority of those microconditions are sitting on trajectories on which the separate entropies of each of those 12 gases are all individually going to rise toward the future. Of course, the number of microconditions on which the entropy of some particular one of those gases goes down toward the future is going to be much larger than the number on which the overall entropy of the 12 of them together goes down toward the future. But both of those numbers are going to be fantastically small. And in both cases, the microconditions in question are going to be scattered, more or less at random, in unimaginably tiny clumps all over the phase space. And the likelihood of the microstate of the system ever wandering into either one of those two different sorts of clumps seems, on the face of it, extremely remote. And I take it that what worries people like Janan and Eric is that this last claim is somehow a little too quick. That although the usual statistical mechanical probability distributions over the initial states of isolated systems plausibly do a good job at ensuring that it's very unlikely that the microcondition of the system ever wanders into the clumps associated with decreasing entropies of the system as a whole, the business of making it unlikely that the microcondition ever wanders into the clumps associated with decreases in the entropy of this or that small and localized and quasi-isolated subsystem is somehow an altogether different matter. The thought, I take it, is that the business of avoiding those clumps associated with entropy decreases in the subsystems may involve imposing the same sorts of initial probability distributions on them as one imposes on the system as a whole in order to avoid the clumps associated with decreases in its overall entropy, and that the relevant probability distributions over the initial conditions of the subsystems might not follow and might even turn out to be incompatible with the initial probability distribution over the system as a whole. And I want to take just a minute to go through a very simple and very idealized example, which is aimed at least beginning to put those sorts of worries to rest. Here's the idea. Consider an isolated system S, which divides at a certain time t into two isolated collections of particles, A and B. Which divides at a certain time t sub 1 into two isolated collections of particles, A and B. Prior to T1, A and B and all of their constituent particles are all in strong interaction with one another. But imagine that at T1, the interactions between the particles in A and the particles in B get turned off. Of course, the interactions between different particles within A are still on, and the interactions between different particles within B are still on, but there aren't any interactions anymore between particles in A and particles in B. Good. So at T1, those interactions abruptly come to a stop. Suppose, moreover, that the macro state of the universe at its initial formation, called at time T0, is some macro state M sub 0. And suppose that at T1, when the interaction between A and B stops, the macro state of A is M sub A and the macro state of B is M sub B. And suppose that all of these macro states, M sub 0 and M sub A and M sub B, are far from equilibrium. And suppose, finally, that the probability distribution over the possible microstates of the universe at T0 is uniform over the region of S's phase space, which is compatible with M0, and uniformly zero elsewhere. Now, there's a familiar argument that comes down to us from Boltzmann, and this is the argument that Janan and Eric and other warriors in this tradition, this is an argument that they're happy to accept, to the effect that the overall entropy of S is overwhelmingly likely to increase in the future of T0 unless or until it reaches equilibrium. The uniformity of the initial probability distribution over the microstates of S, which are compatible with M0, by the way, is a great deal more than Boltzmann's argument actually needs. The fact that the clumps in which the overall entropy does anything else are as tiny as they are and as scattered as they are means that almost any even remotely well-behaved distribution is going to do the trick here. But suppose, just to keep things simple for the moment, that the distribution we start with is in fact the uniform one. It turns out, notwithstanding the unassailable fact that, as Janan puts it, you can't, as a general matter, move from a property of the whole to a property of its parts, it turns out that exactly the same sorts of conditions are plausibly going to obtain, and exactly the same sort of argument can plausibly be run for A and B separately, beginning at the later time T1, when they separate from one another. Here's the crucial point. So here. It'll help to write this. So, oh, I'm sorry. Oh, okay, sorry. So here's the phase space of S, okay? Suppose that, that this is the macro state that the total system S starts out at t equals 0. There's a uniform probability distribution over that initial macro state. At some point later on, at T1, when A and B separate from one another, suppose that the macro state of the total system corresponds to this, okay? And what we're going to have here is a highly filabrated distribution that fills up a very, very small percentage of this total volume, but because of its high filabratedness, sort of insinuates itself into every reasonably sized part. Right? So there's some probability distribution like this. Okay? And suppose that we've organized things so that, for example, this set of dimensions here is the set of dimensions of the phase space corresponding to subsystem A, and this orthogonal set of dimensions here is the set of dimensions corresponding to the other subsystem B that have just separated from one another. The cute thing to notice here is that although this distribution over the phase space of the total system is highly non-uniform, the sorts of expectations about the shape of this filabrated distribution that Boltzmann's arguments are going to suggest, okay, is such that if you look at, say, the probability of a certain microstate of subsystem A, that's going to correspond to an integral of the probability distribution over this line, okay? And you look at the probability of another state of subsystem A, which is going to correspond to an integral over the probability distribution over that line, those are very plausibly going to be equal to one another. That is the best guess one can make given the kind of filabrated distribution that the standard Boltzmann argument leads us to expect, is that in fact these two are going to be equal to one another for any two such microstates, that in fact the probability distribution over A is going to be more or less perfectly uniform in an idealized case like this, and similarly for the probability distribution over B. Okay. So do I still need this mic, or? Okay, sorry. Good, so just to repeat that, the crucial point is this. Although the probability distribution over the possible microstates of the entirety of S at T1 is going to be uniform only over a highly filabrated region within the macrostate of the universe at T1, and not over that macrostate as a whole, the probability distributions over the possible microstates of A and B separately, which that highly filabrated universal distribution induces, are plausibly going to be exactly uniform over the entirety of MA and MB. To see this, consider the diagram I just drew.
Does that mean each one has come to thermal equilibrium?
No. These are supposed to be highly non-equilibrium macrostates of A and B separately. But the probability distribution over the microstates compatible with those non-equilibrium macrostates is going to be the uniform. Okay. That is exactly the one that the simplest version of the standard Boltzmannian argument wants. Okay. Good. And what the usual statistical mechanical expectations about the shape of the highly filabrated universal distribution are going to suggest in a case like this is that for any two microstates alpha and beta, which are compatible with MA, the integrals over the corresponding line should be more or less exactly equal to one another. And for any two microstates gamma and delta, which are compatible with MB, the integrals over those corresponding two lines should be exactly equal to one another as well. That, once again, is a good deal more than we actually need, at least in the, That, once again, is a good deal more than we actually need. But nature apparently does us the favor, without any additional prodding, at least in the idealized case under consideration here, of giving it to us anyway. And the more general lesson here, I take it, is that the business of integrating out whatever microscopic correlations may have built up between the various presently isolated subsystems of the world during the time when they were in interaction with one another is going to tend to make the probability distributions over the microconditions of those subsystems smoother and better behaved and more obviously suitable as premises for the standard Boltzmannian argument than the much less uniform probability distribution over the microconditions of the system as a whole is. And if all that is right, Then the business of embracing the application of those arguments to the system as a whole, but at the same time worrying or puzzling or suspending judgment about their application to its various quasi-isolated parts, begins to look a little paranoid. But once again, maybe I've misunderstood something here, and part of the reason for bringing it up here is to see if that's the case. Good. Now let me go on to the question that I most wanted to talk about today, which is the third and the deepest and the most interesting and the most amorphous and the most phenomenological form of this general puzzlement about the Boltzmannian project that I mentioned at the outset. There's a bunch of ways to put this. Let me put it in a sequence of four increasingly focused and concrete and increasingly tractable ways until we finally get to one that maybe we can say something concrete and explicit about. So, first form. How can it seriously be imagined that my own sense of the passage of time, how can it seriously be imagined, for example, that my own sense, and this is the way that Tim Maudlin has put it to me, that my own sense right here and right now of whether some particular baseball happens to be flying towards me or away from me is somehow anchored in the lowness of the entropy of the world 15 billion years ago. Second form, how can it be, how can it work that the increase of the entropy of the world or of myself somehow constitutes the standard or the yardstick against which I judge the direction in which events are unfolding? How is it, that is, that the entropy gradient of anything ever comes into the picture? I'm certainly not aware of checking on the entropy of anything in the course of deciding whether the baseball is flying towards me or away from me. No comparison with anything else, so far as I'm aware, is involved. I simply, directly, unmediatedly see that the baseball is flying either towards me or it's flying away from me. 3, consider the sense of the direction of time that's implicit in the operations of, for example, a simple mechanical realization of a Turing machine, or an approximate mechanical realization of a Turing machine. Are you asking me to believe, the questioner says, that the thermodynamical characteristics of the world somehow play a role in the way that a machine like that distinguishes between what it has just done and what it's supposed to do next? How so? How can that be? How would that work? Machines like that can apparently function perfectly well. Machines like that apparently have no trouble at all distinguishing between what they have just done and what they're going to do next, without the aid of special devices for measuring the entropy gradient of the world or of themselves or of anything else. 4, consider, finally, a simple mechanical device which has no other business than distinguishing between what it has just done and what it's supposed to do next. The paradigmatic distinguisher, the distinguisher par excellence between what it has just done and what it's supposed to do next. Think, that is, of a clock. And think, for the sake of concreteness, for the sake of simplicity, of an old-fashioned, fully mechanical pendulum clock. Good. Now we have our hands on something we're in a position, I think, to analyze in detail. Note that in the course of the normal and intended operations of a clock like that, there are going to be moments, the moments in particular when the pendulum is precisely at the apogee of its swing, when every last one of the macroscopic moving parts is fully at rest. Note, to put it differently, that in the course of the normal and intended operations of a clock like that, there are going to be moments, the moments once again, when the pendulum is precisely at the apogee of its swing, when the macro condition of the clock in its entirety is invariant under time reversal. And consider how it is at such moments that the clock manages to distinguish between what it has just done and what it's supposed to do next. The macro condition of the clock, together with the microscopic dynamical equations of motion, together with the statistical postulate, is manifestly not going to do the trick. Because if the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, makes it likely that the clock is going to read, say, 3:05 5 minutes from now, and if the present macro condition of the clock is invariant under time reversal, which it is at these moments, then the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, necessarily also makes it likely, and to exactly the same degree, that the clock is going to read 3:05 5 minutes ago as well. And all there is to break the symmetry, all there is that stands in the way of the clocks having read 3:05 5 minutes ago as well as 5 minutes from now, is the past hypothesis. The clock's ability to distinguish between what it did last and what it's to do next, and your ability, presumably, to distinguish between a baseball's flying towards you and a baseball's flying away from you, is damn well anchored in the entropy gradient of the universe. If we were to hold the present macro condition of the world fixed and move the past hypothesis from the beginning of time to its end, the clock would run backwards. Period. End of story. Simple as that. Things like projectiles keep track of the direction in which they're supposed to be moving in a way that has nothing to do with entropy. Projectiles, more particularly, keep track of the direction in which they're supposed to be moving in their momenta. Imagine, for example, a clock that consists of a projectile moving freely at constant velocity along the edge of a ruler. Insofar as the normal and intended operations of a clock like that are concerned, the entropy gradient of the world is at best irrelevant and at worst an inconvenience, a potential source of error, something to be minimized or corrected for. But pendulum clocks aren't like that. The operations of pendulum clocks and of Turing machines and presumably of human brains and of almost everything else that can be used to distinguish before from after are entirely another matter. It turns out to be essential to the intended functioning of a pendulum clock, although it doesn't look like it at first when you look at its design, or of a Turing machine or of a human brain. It turns out that is to be precisely the opposite of an irrelevancy or an inconvenience or a potential source of error, that these systems are in thermal disequilibrium. A pendulum clock, no less than a puff of smoke or a block of ice, is, among other things, an instrument for measuring the entropy gradient of the world. A pendulum clock, more particularly, is an instrument whose hands move clockwise at a fixed number of ticks per minute in the temporal direction that points away from the past hypothesis. Thanks. That's what I have to say.
Thank you, David, for keeping to time especially. Let's begin, Bob.
Thanks, Bob Wald. On this clock example that you were discussing at the end, which I've not heard before, so I should make sure that I understand the gist of it. I mean, the functioning of the clock is critically dependent on the fact that you've started it in an incredibly low entropy state. Namely, this pendulum has absolutely no reason to have that huge amount of energy compared to its degrees of freedom.
Oh yeah, that's
so,
of course
So
true.
you need, in order to have your clock, to have an initial extremely low entropy state that you'd never have had access to without this past hypothesis.
No. That's of course right. The point here was that you know, of course, to have any well-ordered assemblage of material particles like a clock is an incredibly low entropy state. The further point that's being made here is that while the clocks the clock's operations, the clock's capacity to know the difference between 5 minutes from now and 5 minutes ago depends on its entropy increasing in the course of its operations.
No, no, it doesn't. You could make the entropy increase as low as you want, and the clock will work even better. The entropy increase degrades it. It's the low entropy initial state that you're feeding off of to set initial conditions for the clock that make it work.
Let's see, I'm not sure if we're disagreeing here or not. Of course it's the case that, any, that like I say, any organized assemblage of material particles represents a low entropy state. Any non-uniform density in the arrangement of particles represents a low entropy state. A further claim is being made here that in the course of the clock's operations, it wouldn't have a way to distinguish between what it does next and what it did earlier if not for the increase of its own entropy during those operations. That the increase of its own entropy is crucial to the way it's operating. And here's the simple proof of that. Imagine a moment when the macro state of the clock is time reversal symmetric.
Yeah,
If there weren't a
way out of equilibrium, of course.
Yeah, way out of equilibrium. This is the standard Boltzmannian argument, right?
All right.
Take a way out of equilibrium macro condition. We know, and suppose that macro condition is time reversal symmetric. We know how that macro condition is going to evolve macroscopically towards the past and the future, symmetrically. This is the standard Boltzmannian argument. Just apply this argument to the clock. If the clock's macro state at a certain moment is time reversal symmetric, and we've chosen to look at a moment when the macro state of the clock is fully time reversal symmetric, then we know how to calculate its past and future from statistical mechanics. And its past and future will be macroscopic mirror images of one another. So that if the clock is going to read 3:05 here, it's going to read 3:05 here if its macro state here is time reversal symmetric. And its macro state here is time reversal symmetric. So, what do you mean? The state of the watch itself.
Mechanism is not going to be time reversal.
Of course it is. It's stationary. No,
the pendulum is stationary. The rest of the mechanism, though, is not going to be time reversal symmetric.
The rest of the mechanism is. Wait. This is an important point.
The watches don't work on the heat that they generate.
Wait a second.
Pendulum
Wait.
motion.
Consider the logic of the argument here. The entire mechanism is stationary at that moment. The entire mechanism, not just a pendulum. All of the gears, all of the ropes, all of the hands are completely stationary. What you've got here is a completely time reversal symmetric macro state. We know what the predictions of statistical mechanics are for a time reversal symmetric macro state. The macro future will be a mirror image of the macro past.
Let's.
Special low entropy state where it doesn't behave according to the rules of.
No, but every clock passes through that state every time it ticks.
Let me just say one more thing. I
Yeah.
can assure you that clockmakers are trying to decrease make their clocks
Yes.
have at least less
Yes,
entropy
but wait.
increase as they function rather than more.
But hang on one second. Look, there's a really simple logical argument in play here. If you want to say that there's something wrong with the conclusion of the argument, you got to tell me where the argument goes wrong. Here's the claim. Every pendulum clock, in the course of every tick, passes through a macro state in which all of its components are fully stationary. So
Let's move on to something different, slightly perhaps.
But this is really important. This is the crux of the whole thing.
Well, you need the interaction with the environment. That's
Yeah, Eric Winsberg.
Yeah.
So I think you understand the worry perfectly well. The worry is about whether the fibrillation that drives
This is the second worry.
Yeah.
Right. This is this worry.
The first one, yeah.
Yeah. The first serious one. Right.
So the worry is of course exactly that whether the fibrillation that drives the Boltzmannian argument for the universe is going to work for all the subsystems.
Right.
The argument, if the argument has any merit, it's not going to work. I mean, it's not going to be a worry when you've got 12, if the system is made up of 12 gases, right?
Right.
The worry is not that if you have something that lives in, n times 12 dimensions, and you go down to n dimensions,
right,
the fibrillation is going to. So the worry, if it's there, is going to be motivated by two considerations. One, that that subsystems are on the order of 10 to the 20 or 10 to the 23 or 20 to the 24 or 10 to the 25 dimensions, and that we have no idea 10 to the how many states the universe has.
Right.
And second, that the dynamics driving it.
But wait.
Yeah,
why do the big numbers make us worry more?
Because it only matters in the sense that you can't derive one's intuitions about the plausibility of the argument by giving me a diagram where you go from 2 to 1 dimensions.
Right. Okay.
Right? I mean, so
that's fair enough.
The sense is that that fibrillation is a kind of mechanism that mixes, sure.
Right.
But how well does it mix?
I see.
I mean, so maybe the worry is paranoid, right? But you can't. If someone is paranoid that the American bureaucracy is out to get them, you can't kind of bring them to a school, and say, look, it's so simple the way, look how governments work. They're so simple. Look at this 12th grade class. Okay, right. Okay.
Right.
So if the paranoia is being driven, it's partly by the number of dimension reduction.
I see.
And it's also partly about the fact that the universe goes through enormous regime changes over the course of its history, right? So that, at least from gravitation to electromechanical or something like that, and before gravitation, who knows? So the worry is that the reasoning there is sort of one regime kind of reasoning.
Okay.
So it's just a worry that toy model doesn't really apply for two reasons.
Right.
Okay.
Right.
Okay.
Thank you.
I'm surprised in the discussion of an arrow of time that you didn't mention the retardation of electromagnetic radiation.
Actually, I think I did. I said the first sentence included radiative asymmetries. Ha.
Well, I'm debating whether to stop here or amplify. But since I've got the microphone in my hand, I'll just amplify one short, which is itself due to a property of the very early universe.
Right.
Not necessarily low entropy, but a low amount of radiation and wavelengths that become visible today. In fact, we're adapted to avoid, if we were sensitive, for example, to 3 degrees, we wouldn't get anywhere. Life would be a complete fog. So part of the reason we have an arrow of time built in is, and I think it's much more important effect than the increase in entropy, is we get most of our information from the past. Thanks.
Any response? Or
No, I think that it's an enormously important asymmetry.
Okay, this is just a really minor point about this thing, the uniform. I mean, if you had, suppose the total system that has 2 parts, one of which has a small number of degrees of freedom, and the other has a big, and you fix the initial energy within some narrow range, and then the 2 things sort of equilibrate, then the smaller system will have a Boltzmann distribution, which is exponential e to the minus energy over
I
K2.
see.
So it won't be quite uniform. So I think you can't claim it's uniform, but
Good point. Thank you. Good.
any more comments or questions?
Hi, Sean Carroll. I just have minor, maybe rhetorical point, because you seem to place emphasis on the fact that the low entropy initial condition was 15 billion years ago,
Right.
as if that's a lot of
Right,
years.
right.
I think that the natural comparison would be to the equilibration time of our Hubble patch,
Yeah,
which,
yeah.
which
No,
might be plausibly estimated as the time when the last black hole will stop evaporating, and that's 10 to the 100 years from now.
yeah, no. I mean,
So we're really, 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 really early in the
I
history of the
agree
universe.
100%. I mean, the rhetorical emphasis on 15 billion was to put you in the mood of the questioner there. But yes, exactly as you said. I mean, the way I proposed, I had just one sentence answering that, which was exactly to say, look, that sounds like a long time, but it's minuscule compared to the relaxation time. Right, right.
See, any other comments or questions?
Just back on the working of watches.
Yeah.
I was hoping that somebody who actually knows would chip in here. I assume that the way the watch achieves the thing that you're talking about is by having some kind of a ratchet.
Yeah, that's
mechanism.
right. A ratchet and a spring.
Right.
Right.
So I assume that that in response to the earlier question, the answer is that the watchmakers, when they're designing the ratchet part, that's the place where it's crucial to their workings that they don't make the entropy decrease too small, because they don't, otherwise the ratchet thing would be bouncing back
Yeah,
up
it depends on
too high again.
scraping
So they need to make some friction as the thing goes down the ratchet.
That's right. And that's exactly right. And also, if you think about the spring will spend a certain amount of time expanding and then stop, okay? So it has a certain amount of momentum. That energy has to go somewhere. It's going to raise the temperature of the spring. Right. Yeah, both of those sorts of effects are going to contribute. And both of them turn out to be crucial because, because if there wasn't an entropy gradient, there wouldn't be a way for it to go. Yeah.
No, but the simplest clock is a particle on a free line.
No, I talked about that.
Or
Yes.
something turning, and you just send it off in the
Yeah,
clockwise
absolutely
direction,
right. Those
and it
sorts of-
keeps going forever.
Absolutely correct. I mentioned that explicitly, if you remember. Yeah,
No.
those sorts of clocks keep track of which way they're supposed to go in their momenta or in their angular momenta if they're turning. Those are almost certainly not the way the clocks, say, in our head work. Okay, and they are almost certainly not the way, and they are certainly not the way things like pendulum clocks work. You're absolutely right. You can construct a clock whose operations have nothing to do with the entropy gradient. They keep track of the distinction between what they did last and what they're supposed to do next in their linear momentum or in their angular momentum in the two clocks that you mentioned. That's absolutely right. That's not the way our clocks work. That's not the way the clocks in our heads work.
No, in a sense it is, because the pendulum is like a piston on a car, right? Piston in a car keeps driving the car forward, not backwards. And
Yeah,
that's because of the way in which the crankshaft is set up, etc.
Wait, no. There's a crucial difference. The crucial difference is whether or not the clock in question ever passes through states that are macroscopically reversible.
Yeah, and it doesn't have to.
Hold on a second. The two clocks you mentioned, the free particle moving along a ruler or the rotating object, never pass through macroscopically reversible states. Their states are always macroscopically irreversible. There's this momentum. Something like a pendulum clock or a Turing machine or us are constantly, with every cycle, passing through a state which is macroscopically irreversible. If you analyze them at that point, reversible, excuse me. If you analyze them at those moments, there's nothing like this momentum to tell them which direction to go in. That's the crucial difference. That's the crucial difference.
So I think we should end, well, let's see, one last comment.
Yeah, Shelley Goldstein. I just want to say that the crucial example used by Feynman in his article on the direction of time was the ratchet and the pawl, which is crucial to this functioning of the pendulum clock. And
Right.
the reason it was his example
Right.
is it is so confusing.
Right.
It was a great thing to focus on because it's such a surprising thing. And that's why
Exactly right.
you're surprised here.
Exactly right.
Thank you. So let's thank David one more time.